Vehicle positions in the I-24 motion system are produced by object detection and tracking. So what we mean by that is we first use a 3D object detector, which is a class of computer vision algorithms that take an image frame as inputs and output a set of object locations. So in our case, an object is parameterized by an X and Y location, which corresponds to the rear, bottom, center coordinate of a rectangular prism that tightly encapsulates the vehicle. Obviously, this is an imagined rectangular prism, but the rectangular prism is parameterized by a length, a width, and a height. And these are all defined within meaningful distance units, such as feet, and then they are projected into the image coordinates. Each object detection also contains a vehicle class and a vehicle ID. If you're interested in the specific computer vision algorithms we use, we're using a RetinaNet detector with a ResNet 50 backbone, and we're training this on a custom dataset. Once we have a set of 3D object detections for a set of frames, we perform object tracking, which essentially is producing a set of tracklets. So a tracklet is a set of object detections, one per frame. And the idea is that the algorithm is supposed to select all of the detections that correspond to a given real-world object and associate them with a single unique ID. There are a number of object tracking algorithms that exist, and we're using a relatively simple one called KIOU, or Common Filter-Based Intersection over Union Tracking, which it is important to note is an online algorithm, which means we only use the set of frames up to frame N to produce the object tracklets at frame N. We do this because we need the algorithm to run quite quickly. So in order to train algorithms or fit algorithms so that they're able to detect vehicles well, we need a data set. And importantly, before we started working on this project, there weren't really any 3D object tracking data sets that would work for us. So we had to manually label a data set of over 800,000 bounding boxes by hand. So this is that data set, which is assumed to be perfect, and then we fit our algorithm so that its outputs match as closely as possible this data set. Okay, so here is an example of our current object tracking performance. In a lot of cases, it's quite good, but we still have challenges at the handoffs between cameras, which is somewhat due to homographies and somewhat due to the changing view on the object. We still have difficulties at overpasses where objects are occluded for a long period of time. And because we have such a large set of cameras, we have to run object tracking in parallel across many different machines. And we have difficulties at the discontinuity between computational boundaries. So when an object is being tracked on one machine and then it is handed off to another machine. If you're interested in working on the object tracking side for vehicle tracking, we have several data sets available on which you can develop and benchmark object tracking performance. We have the I-24 multi-camera 3D dataset from which this video data is a part, and that is published in the British Machine Vision Conference Proceedings for 2023. We also have a dataset about to be published in the Winter Conference on Computer Vision Applications, and that dataset includes 1 hour of video data from over 200 cameras in the I-24 motion system, and also includes GPS trajectories against which you can validate the performance of object tracking algorithms. It's important to note that object tracking is still a field of active development on the I-24 motion system, so we're constantly working to improve the quality of our tracking performance, which in turn is going to produce data that is more suitable for micro-scale simulation or model fitting or any sort of micro-scale analysis you might want to do with the data.